In first semester chemistry, you probably learned that an acid-base reaction is one where an acid and a base come together to form water and some ionic compound. And if you had a really good teacher, which most of you did, you learned that that ionic compound goes by another name. Ionic compounds also are called salts. So you learned that an acid and a base come together to form water and a salt, and you called this a neutralization reaction. Because we taught you that acids and bases neutralize each other to produce a neutral solution. And we lied to you. Because that salt that forms is not always going to allow this reaction between the salt and the water is not always going to allow for the pH to be 7. Some salts, however, will be neutral. Some will be acidic, and some will be basic. And the way that you determine if a salt is going to be acidic, basic, or neutral is to think about what went into that salt. So, for the purpose of this, you think of it kind of like a fight. The fact that some salts can hydrolyze with water to produce an aqueous solution with pHs other than 7 is called hydrolysis. It's water splitting. And we're going to think of it like a fight. So you think in your head, anytime you get a salt, so let's take our good buddy sodium chloride. What base and what acid came together to form this salt? Well, by definition, a base is something containing hydroxide, at least according to Arrhenius. Again, that's not always the case, but in the case of sodium, it was probably sodium hydroxide. And chloride must have came from somewhere, so it must have come from maybe hydrogen chloride, so that's HCl, which I hope you remember is a strong acid. So let's think of this as a fight. If I have sodium hydroxide, hopefully you know sodium hydroxide is a strong base, and hydrochloric acid, which is also a strong acid, if these two got in a fight, strong and strong, they're going to completely annihilate each other. There'll be blood, guts, and gore on the wall, but there won't be anyone around afterwards. They'll both knock each other out, and this will produce a neutral solution, or relatively neutral. When you have a strong and a strong, you have to look at their Kas and Kbs. What about sodium acetate? Well, sodium must have came from sodium hydroxide, which is a strong base, and acetate must have come from acetic acid, which is a weak acid. In a case of a fight between these two, the strong base is going to win and kick the snot out of this weak acid. So in this case, Ka would be much greater than Kb, and we would produce a basic salt. If we have a weak base, like ammonium, and a strong acid, like hydrochloric acid, they would produce a acidic salt, like ammonium chloride. Because once again, the strong acid, having a high Kb, is going to kick this, having a high Ka will kick the snot out of a weak base with a low Kb. If you have an acid and a base of comparable strength, both are weak, both are strong, you need to look at the Ka or Kb. Sorry, the Ka and Kb. If the Kb is larger, it's basic. If the Ka is larger, it's acidic. So again, you can think of this as Ka versus Kb. The stronger will always win. So let's see this in action. We're going to predict whether or not these salts are acidic, basic, or neutral, and then show an equation that will back up that prediction. So, the first thing you do is look at the salt and ask yourself which acid and which base reacted to form it. Sodium acetate, that would be sodium hydroxide and acetic acid. Which one is strong and weak? Sodium hydroxide, strong base, Acetic acid, weak acid. The strong always wins, so strong's going to kick the snot out of this poor weak acid, and it's going to leave the poor weak acid to do all of the work. So we agree that this is going to be a basic salt. If we predict it's a basic salt, we have to state that in our equation. So basic salts will produce hydroxide, acidic salts will produce hydrogen, so since this is a basic salt, we're going to produce hydroxide. So let's start by writing that. The strong whatever, either strong acid or strong base, in this case we have a strong base, becomes a spectator. Enjoy the fact that strong and spectator both start with S. Alliteration is your friend. So the strong base, sodium, becomes a spectator, leaving acetate as the only other thing left to react with. So let's go ahead and include that in our equation. What is that acetate going to react with? Well, this is hydrolysis, so chances are we're talking about water. And since this is an aqueous solution, water is the only other thing left in this reaction. So let's go ahead and include water as a reactant. If you're paying attention, my structural formula is wrong. This oxygen doesn't have a hydrogen yet. It's about to take one, though, from this water. So that's going to be our product. So our formula proves that this salt is a base. Alright, what about sodium nitrate? Well, ammonium nitrate. Ammonium nitrate would have to have been made by ammonia and nitric acid. We know that ammonia is a weak base. Nitric acid is one of your 6 strong acids. Strong acid kicks the snot out of the weak acid and the strong acid kicks the snot out of the weak base and leaves the weak base to do all of the work. So since we know that this is going to be an acidic salt, we know we're going to produce hydrogen. So let's go ahead and write that. Ammonium is going to have to react with something, must react with water. Now when it comes to ammonium and any of its cousins, like potassium trihydride or whatever, it's often easier just to say hydrogen is the same as hydronium, so I'm going to change that, and that'll make balancing this much, much easier. So now it's easy to see this ammonium donates a hydrogen to water to become ammonia. Or if you're confused, it's okay. The formula will make sense in a minute. And this formula therefore proves, or this equation therefore proves, that this is an acidic salt because we are producing the hydroxide, or the hydronium ion. So let's do one more like what you're going to see on the AP exam. While the previous might have been a multiple choice question, this is more like your calculator section. Calculate the pH of a 0.1 molar solution of ammonium chloride. The Kb for ammonia is 1.8 times 10 to the negative fifth. So first off, I have ammonium chloride. I need to figure out, is that an acidic salt, basic salt, or neutral? Ammonium is a weak base. Hydrogen chloride, or hydrochloric acid, is a strong acid. So strong wins out, and this is going to be an acidic solution. So the ammonium ion is going to give up a hydrogen, become ammonia, and the hydronium ion. Every time I say hydronium, I want to say hydroxide. Okay, so this is going to produce an acidic solution. So we need, we're giving Kb. They're being sneaky. Very, very sneaky, because we're producing an acid here. So we need to have a Ka. So remember that Ka and Kb are related through Kw. Ka times Kb equals Kw. And you remember that Kw equals 1 times 10 to the negative 14. So if you divide those two out, you find that Ka is actually 1.39 times 10 to the negative 11th. So now that we have a Ka, we can go ahead and do our rice table for this. And you guys have done so many rice tables and time's short, so I'm just going to make it appear on the screen. Abracadabra. So we know that Ka equals the concentration of a hydronium ion times ammonia divided by ammonium. And if we know that Ka equals that, we know that Ka equals x squared over 0.1 minus x. And Ka is 1.39 times 10 to the negative 11th. Since x here is going to be infinitesimally small compared to 0.1, it can be neglected. So we're going to neglect this x. And all we're left with is some easy math. We find that the concentration, we find that x equals... Oh, crap. I just realized I'm pulling my problems from the wrong place. So if you've been following along and you went, where did he get this Ka from? Because my Ka is coming out to be something different. Don't stress out. It's my mistake. Let me fix it really fast. You won't even notice. Okay. That's better. Again, I'm sorry if you've been following along. This is the actual Ka. If you really want to know, I was pulling from exercise 21. We're actually doing exercise 22. Alright, so 5.56 times 10 to the negative 11th times 0.1 is 5.56 times 10 to the negative 11. The square root of which we find that x equals 7.46 times 10 to the negative 6. And that is also equal to the concentration of the hydronium ion. And since pH is the negative log of the concentration of hydrogen or hydronium ions, we find that our pH is actually equal to 5.13. At the very last section of this unit, last section for this segment of notes, is the Lewis concept of acids and bases. Which you remember from the previous video, then acid, according to Lewis, yes, Lewis, the same guy that gave us the Lewis dot structures, the ones you see here, he was actually working on acids and bases, and he developed the Lewis dot structures to show this. He said that an acid accepts a pair of electrons, again, alliteration is your friend, acids accept, while bases donate. The most famous Lewis acid is boron tri-anything, but boron trifluoride is the most classic example. Boron trichloride is a Lewis acid because it can accept a lone pair from another compound that has one to spare. So it forms a coordinated covalent bond, meaning that nitrogen donates both of the electrons needed to produce a bond with boron. So anytime you see boron and anything, any three things, so either halogens or hydrogen, that's an Lewis acid because boron is willing to accept another lone pair. Next class we'll go over we'll do practice problems of this, but exercise 24 and 25 in your packet also cover this. In fact, that's the ones we'll be doing in class.